If you are new to Fronius, then you're absolutely right here. A very warm welcome to the webinar series Get Successfully Started with Fronius. This is part 2 of the series. Part 1 already aired in November and maybe you have watched it. We gave you an overview about the products and the solutions that Fronius is offering. And today in part 2 we will go a step further. We will take a look at system design, how modules can be connected on the roof, what you need to pay attention to, and in the end I want to give you an overview about the necessary components for a successful installation. Already I'm using this moment to announce part 3 of this series. If you like it and if you're interested, part 3 of Get Successfully Started with Fronius will air at the beginning of January. So you will find the opportunity to register for this webinar in December. Let's start with system design. As you know, a PV generator consists of several modules. And those modules, they are connected with each other, and this connection can be done in 2 ways. On the one hand, they can be connected in series. And in this way, the current remains equal and voltage increases with every module that is added. In parallel connection, it is the opposite. So then the voltage remains equal and current increases with every module that is added. When I started getting into this topic, I was a bit confused about those 2 types of connections, and I didn't have a picture in my mind how this applies to the modules. And I want to give you an example, and then I hope that it's getting more clear for you. And let me do this by drawing a bit on the flip chart. We start with a serial connection. So these are our modules. The modules, they are connected with the inverter. And we assume that each of those modules, they are carrying 10 amps and 40 volts. And this is true for all of them. I hope you can read my writing. In this case, as we said, in serial connection, the amount of amps always stays the same, no matter how many modules are connected. So in this way, at the inverter, there are also 10 amps. The voltage, however, is added up. So at the inverter, we do have 120 volts. So in this way, if the modules, if they are connected in series, you can add a large number, or let's say almost infinite number of modules, and in this way you will never increase the number of amps, only the voltage. Let's assume we add a parallel string, and again we have 3 modules here. And those modules as well, they carry 10 amps and 40 volts. In this way, the amount of volts stays the same and only the amount of amps is increasing. So then it's 10 plus 10 amps equals 20 amps in our PV system. The inverter gives you a window of possible amps and possible voltage. In our case, if we're using a Gen 24 Plus, then there are 2, let's call it connection points. They are called actually MPP trackers. I will tell you in a minute what this is. So those 2 connection points, one carries up to 22 amps and the other one up to 12.5 amps. And the inverter also gives you an a number of, or a window of possible voltage, and in our case this is 80 to 1000 volts. So if we had a PV system like this, we would stay well inside both of those restrictions. And in our case, it's 20 amps times 120 volts equals 2400 watts. I said that those two connection points, they are called MPP trackers. MPP trackers stand for maximum power point trackers. And the maximum power point is called maximum power point because it's the point where watt is optimized. And the inverter chooses always for those two connection points separately, it chooses the perfect amount of voltage that maximizes the watts. It is not always the case that a high amount of volt equals a high amount or a higher amount of power. In many cases, volts increase and amps decrease. And it is always the task of the inverter to find the perfect working point, so the perfect amount of voltage. Now you will ask, what can be reasons that these two parameters, amps and volts, are changing? I will tell you. I will go back to the slides and I will show you the two most important impact factors on amps and voltage. The first thing you need to pay attention to is irradiation. Irradiation has, you see it in this graphic on the left hand side, has a huge influence on the amount of amps and less influence on voltage. You see the top curve, the red curve. This is the production line when a lot of sun is shining, when irradiation is high. And you see on the bottom, the black curve, this is the production curve when irradiation is low, so on a cloudy day, for example. Those points you can see here, those are the maximum power points. So those points, they are the amount of voltage that maximizes power in the end. So it is the task of the inverter to find these maximum power points. What you can see here is that irradiation changes, as I said, amps a lot, but it doesn't change this maximum power point a lot. Slightly, of course, but not very much. It is the other way around with temperature, and this is a second very important impact factor. Again, you see a graphic on the left-hand side, and you see different production lines. On the very left, you see the red line. This red line corresponds to very high temperature, and on the right-hand side, you see the blue line. This one corresponds to low temperature. With high temperature, the maximum power point is at rather low voltage, and in the blue production line, the maximum power point is at very high voltage. And you also see that the maximum power point changes regarding amps, doesn't change a lot, but regarding voltage it does. And again, it is the task of the inverter to find this maximum production point. With our inverters, you get a lot of flexibility regarding design. I told you those two MPP trackers and this large span of possible voltage, 80 to 1000 volts. So you can actually create very long module strings and connect them to the inverter. Those two MPP trackers, so the inverter is finding the maximum power point for two connections separately. So when you are designing a PV system, then it is your task that all the modules that are connected to one MPP tracker, that they have similar irradiation and similar temperature during their production. You see here on the right hand side in this picture, you see this house, and you see that this house has a lot of modules south side and also a module field west side. a module field like this you can easily connect to our inverters. And it is perfect that the south side is connected to one MPP tracker and the west side is connected to the other MPP tracker. Overall, the PV generator can be of a size of up to 150% of the inverter size. So an inverter of 10 kilowatt can be connected to a 15 kilowatt peak PV generator. Regarding connection to MPP trackers, what you can do is to connect an east and a west side field together at one MPP tracker. You can do this if in condition of a few things. So the module string has to be the same size, the modules have to have the same characteristics, and no shadowing has to be there. East-west, is very common and very popular, and not without a reason. You see here on the left-hand side the production curve of east-west PV generator, and you can see in the morning this kind of belly to the outside. So you have more production in the morning and also more production in the evening. And the only downside is that at noon there is less production. Usually there is too much production anyway at noon, so it doesn't matter if there is a little bit less production, and people are happy if in the morning hours and in the evening hours that they have more PV power available. Let's go to the second chapter. Let's go to a PV's nightmare, to shading. I mentioned it before, shading is a problem. It is a problem because it decreases the production. And secondly, it is also harmful to the modules. Why is there shading? Because of quite obvious reasons. There can be some roofs that are giving shadow, trees of course, but also things that you may not think of, like dirt, like leaves in autumn or snow in winter. So only because there is no roof or no tree that is giving shadow to your PV system doesn't mean that you do not have to deal with shadowing. In the first place, rule number one is no shadow is always the best shadow. However, if shadow occurs, then there are also some ways you can help yourself. Before I show you the solutions, let me show you how shadowing is causing problems. And again, I will do this by drawing a sketch on the flip chart. We start with a module generator connected in series. Again, there are 3 modules. They are connected in series and they are connected with the inverter. Again, we assume that each of those modules, they're carrying 10 amps and 40 volts. And this holds for all of them. 10 amps, 40 volts. So in this case, at the inverter, there are also 10 amps and 120 volts. And this equals power of 10 times 120 equals 1200 watt. And now imagine that one of these modules is affected by shading. Imagine it like this. And you also remember from before that less irradiation means less current. It doesn't have an effect or only minor effect on voltage, but a lot on the current in this module. So in this case, we say that this module is not carrying 10 amps anymore, but just 2 amps. For simplification, we assume that volts, they stay the same. And in a serial connection, there is the rule that always the weakest part of the chain counts. So in this case, because this one module is only carrying 2 amps, we do not have 10 amps here at the inverter, but also 2 amps. And you can imagine what this means for our overall power. Suddenly it's not 10 times 120, but only 2 times 120. And this now equals 240 watts. What is more, shadow is also harmful for the module. You have to imagine that this is like a bottleneck. So the power, the current from those two healthy modules has to go through this affected module. And this is causing heat and also causing damage to this shaded module. Good news is there is a solution to this. And first of all, this solution can be found in the modules themselves. Modern modules, they have diodes integrated, and they are realizing if there is shadow, and they are switching on in order to bypass this damaged or this shadowed module. So in the case of shadowing, this happens, and the affected module is not the bottleneck anymore, but is switched off from the generator. What would this mean for the power? So again, we have 10 amps times, this time not 120, but only because of those two 80 volts. But still, this equals 800 watts. And good news still hasn't finished. There are some other ways that will improve the situation. Let me show you this in the slides. In modern modules, you have those diodes not only in one per module, but one per module string. You see here in this graphic, you see 5 modules, and each of these modules consists of 3 strings. And each of these strings can be bypassed in the case of shadowing. So as you can see here, one module string has shadow on it, and then this one string is bypassed, and the other strings of the affected module, they are working as always. So this means that there is only a little bit of reduction of power, and moreover, this bottleneck effect is minimized. And you can even go one step further, and you can not only use standard modules, but half-cell modules. What are half-cell modules? They are basically the same as the standard modules, only that they have the double amount of module strings. So imagine, like you can see here on the right hand side, imagine some shadowing. You could, instead of this cloud, imagine snow in winter. The snow is melting, is going down on the module, and is then freezed on the bottom side of the module. And if you had standard cells, then there would be zero production, because each of the strings is affected. If you have half-cell modules, then you see that only the bottom part is not working, but the upper part can produce as always. Besides the modules that help you dealing with shade, there is also a solution that Fronius is offering. And this solution is called the Dynamic Peak Manager. Dynamic Peak Manager means that those maximum power points, they are always found also in case of shadowing. Imagine that in finding this maximum power point is very complicated with shadowing. Imagine there is a module field and some modules are switched off, some modules are running half, and half of their cell strings, they are turned off. And so it can happen that it is very difficult to find this maximum power point. You see here in this graphic, you see this blue line. Blue line is the non-shaded case. And in this blue line, this is very simple. It goes up, there's a peak, and then it goes down. And the inverter doesn't have to work a lot to find this maximum power point. But with shadowing, this production line can become more difficult and can look like the red or the black line. So in this case, there are several peaks, and the inverter has to find the global maximum and not stay at the local maximum in order to maximize production. Our inverters, the Fronius inverters, they are they are going over this whole line. So they're going from 200 volts to 300 to 400 to 500. The inverter is checking every point of voltage and is recognizing if there is a local maximum and a global maximum. And in the end, with the dynamic peak manager, the inverter stays at the global maximum. System design is very complicated. You can find some help in our planning tool. This is the Fronius Solar Creator. You find this tool free on the internet, so you can use it anytime and free of charge. What can you do there? You can design your module field. The Solar Creator gives you advice on the best inverter you take, can simulate the use of an ohm pilot, a watt pilot, or a battery, and it also helps you with the installation. Let's go to the third part of this webinar. The last part, we go to the required components. I used the Solar Creator in order to do this diagram. So the Solar Creator actually is doing the diagram for me. And as you can see, I created a PV system with 2 module strings. Once this is a 8 module string and the other time a 7 module string. Both are connected to the inverter, and I also connected all the other Fronius devices. So an ohm pilot, a watt pilot, a battery, a smart meter. And using this diagram, I will now create a shopping list for you. So I will show you the components you need for your first successful installation. You need at first the basic components. So this is the Gen 24 and the smart meter. A smart meter is basically not mandatory, but it is recommended strongly. Only with a smart meter you can use the visualization in SolarWeb. And at latest, if you are using a battery, ohm pilot, watt pilot, then there is no way around a smart meter. And then depending on the PV system and on the desires of the customer, you need the other components, ohm pilot, watt pilot, or our battery solutions from BYD or LG. Besides the components, you need DC cabling, so the cabling from the modules and from the battery, as well as SPDs. Where you have to build in these SPDs, please check this beforehand. This varies from country to country. In Austria, you need an SPD after roof entrance and before the inverter. Then you need AC cabling, of course, to connect the inverter and all the other devices. You need Modbus cabling for communication. All our devices, they are communicating with the inverter except for the watt pilot. The watt pilot is using Wi-Fi. And then for the watt pilot, you would need a Type 2 cable. This is the connection between watt pilot and an electric vehicle. As I said, the watt pilot is connected via Wi-Fi, so please make sure that there's a strong internet connection to the place wherever you install this watt pilot. And in order for this internet connection to be good and strong, it is recommended that you have Wi-Fi repeaters or power line adapters with you. In many cases, or we know from many, that the installers, they're going to the customers, they're installing the watt pilot, and then the internet connection is not enough in the garage or wherever the watt pilot is fixed. If you use a Fronius ohm pilot, please remember to take with you a temperature sensor and a heating rod, 3-phase, maximum 9 kilowatt. If you are having a battery solution, then please make sure that you have a backup switch with you. You can use an automatic or a manual backup switch, or if full backup is not desired, then you can also do a PV point. Let me sum it up. So the shopping list, the must-haves are the devices, the generator in the correct power class, smart meter. If you need, there's also the option of a smart meter IP. This smart meter is using current transformer CTV, and they can connect also via Wi-Fi, so they do not need Modbus cabling. You need DC cabling and SPDs according to the regulations in your country. AC cabling, typically it's 5 times cross section 2.5 to 4 square millimeters. And please also have with you an AC circuit breaker, 4 poles, 60 amps to 25 amps. Optional shopping list consists of all the devices you might want to include, but you do not need to. So first of all, this is an ohm pilot. When you're doing an ohm pilot, please have with you a temperature sensor and a heating rod. As I said, 3-phase, maximum 9 kilowatt. Also AC cabling, of course. Watt pilot in the types of home or to go. Type 2 cabling for connecting the electric vehicle. And please make sure that the internet connection is stable. And if you're installing a battery, BYD or LG, besides the cabling, you need the correct backup switch. So either automatic, manual, or if none of those, then the PV point. We are coming to the end of this webinar. I hope you enjoyed it. As always, the recording will be forwarded the next days. Again, this was part 2. If you're interested in part 3 and all the digital side of your first installation, then please tune in again. Part 3 will air at the beginning of January. Also recommended is to visit our YouTube page. There you find already recorded webinars and also how-to videos. Again, I hope you enjoyed it. I did. It was a pleasure for me. Thanks for watching, and I see you next time. Bye-bye.